This video is a three-part series on a seismic retrofit standard used throughout the San Francisco Bay Area called Standard Plan A. Now, the organizations behind me here are the organizations that put it together. That's the Association of Bay Area Governments, Earthquake Engineering Research Institute, Structural Engineers Association, building officials, etc. So it's been well vetted. A lot of people came into the making of it. There's one logo that's not here, and that happens to be Bay Area Retrofit. I was also on the committee and know the entire system that it uses extremely well. Now, I'd like to point out this is a very, very important document. It's been used by the California Earthquake Authority. The city of Berkeley also finances retrofits with this. The city of San Leandro teaches a course to contractors and homeowners. And it's used throughout the Bay Area. City of Hayward actually is starting to require its use. So it's, it came out about 2006, and so it's been almost 14 years that it's been used extensively throughout the San Francisco Bay Area, and literally millions of dollars has been spent, much of it public money. So if tens of millions of dollars are being spent by the public as well as by private individuals to protect their homes using this particular standard, you would really want to make sure that it is as effective as it can possibly be. And so the purpose of this three-part video is to see if it is as effective as it can be and if it needs any improvements. Now, right now, we're going to go over some basics. In order for you to understand Standard Plan A, you need to understand some basic concepts. So we're going to go over what foundation bolts do. We're going to go over what plywood does, and also something called shear transfer ties. Once you have that basic information, then I'm going to compare two houses. And one of them I'm going to use Standard Plan A, and one of them I'm going to use a custom design system, which is what we use. And the Standard Plan A one, you're going to see how it takes almost twice as many retrofit components compared to one that is custom designed like we normally do, and it's based on science. Then for the rest of the video, which is, I don't know, about 25 more minutes, it's pretty long, I'm going to show you the science behind what I'm telling you and why, and I'm going to prove to you that what I'm telling you is true. So let's go ahead and take a look at the basics, and we'll go from there. So the main purpose of Standard Plan A is to prevent the damage to homes that have cripple walls. Cripple walls, they caused a lot of damage in previous earthquakes when they collapsed. A lot of homeless people, a lot of people lost their lifetime savings. And I'm going to show you exactly how Standard Plan A attempts to do that. So the first thing we need to understand what a cripple wall is. This wall right here is a cripple wall, and it's a wall that's between the foundation and the floor that you walk around on, and if they collapse, you can end up with this situation right here. So this is the floor of the house where you would be walking around on in the house, and it's rocking back and forth like that. And let's say the house weighs 100,000 pounds. It rocks back and forth, and it just can't handle that much weight rocking on top of it, so the wall collapses. So the point of a cripple wall retrofit is to make sure that this wall is strong enough so that it does not collapse like that and keeps the house attached to the foundation. Now, this is what happens when they fall off the foundation. So you can see here, there used to be a set of stairs, or there are a set of stairs that go up here to the front door, but the floor is actually way down here, so you can tell it probably fell 3 or 4 feet off of its foundation. And so this house right here, actually, I was the FEMA inspector who came in and looked at this house after the 1989 earthquake, and it was a big mess. I mean, the plumbing was torn out, the plaster was everywhere. It was, it's obviously just really screwed up, and it was even more screwed up on the inside. And so I went over and I did the documentation I had to do, and then I came by a week later and the house was gone. They had bulldozed it, hauled it away, and the people who had lived there, I don't know what happened to them, but there's probably a house there now, but they lost it. And the point of Standard Plan A and these government bodies putting Standard Plan A together is to keep homeowners from having to go through this ordeal by giving them something simple to work with that uses these, the plywood and the bolts and the shear transfer ties that we just looked at in an intelligent way to make sure that they can get their houses retrofitted properly. So we're going to be looking at all the, basically what they're trying to do, and then primarily we're going to be looking at the plywood connection, because that's the number one factor in a good retrofit is a good plywood connection, and most of this video is going to be about that. So right now we're going to go into the technical parts of Standard Plan A. So remember, this right here is the cripple wall, and we're going to try and keep that from collapsing. Now this is the cripple wall in its entirety if you were to be underneath the house looking at it. Here's the floor that you walk around on. This is the cripple wall itself, and this is the foundation. And we're worried about this piece of wood right here sliding on top of the foundation, and we fix that with bolts. The other thing we're worried about is this piece of wood called a floor joist sliding on top of this piece of wood, which is called a top plate. Now let's go ahead and see how that's done. So if you come over here, you'll see that here's the cripple wall. It's just, standing there like it's supposed to. Then the earthquake force comes this way and it tries to knock it over like that. And it's a pretty easy solution. All you need to do is put some plywood on the cripple wall, and that solves that problem. Now the next one we have here is the bolts. So this is the mud sill. It's just sitting right here, as you see it right here. So remember, that's the bottom of the cripple wall. Earthquake force comes this way, tries to push it off like this, and then we simply bolt it to the foundation. Now on the top, we have the same problem with sliding. So here's the floor you walk around on. This right here is the floor joist. And we want to make sure that when the earthquake force tries to push against it, it can't move. You see how this dotted line show how it's moved moved a foot or so. We want to make sure it doesn't move. And so we use these are called shear transfer ties. And you can see right here, that's a piece of metal here and a piece of metal here and a piece of metal that will keep that from sliding when an earthquake hits. So in summary, we're going to keep the cripple wall itself from collapsing by putting on plywood. We just nail some plywood to it. The next thing is we're going to keep our cripple wall on top of the foundation by bolting this piece of wood called a mud sill to the foundation. We do that right here with the bolts. And finally, we're going to keep the floor that we're worried about moving onto the top of the cripple wall by putting pieces of steel right here connecting this piece of wood to this piece of wood, as shown right here with the shear transfer ties. Now Standard Plan A, what it does, it gives a system by which we can take any house and figure out precisely how many linear feet of plywood we need, how many bolts, and how many shear transfer ties. And we're going to go ahead and look at that part right now. And this is the technical part, and this is the part where you're going to see a lot of problems. In the world of seismic retrofitting, we're always talking about pounds of force that are pushing against a house and the pounds of resistance to make sure a house does not fall off its foundation. So let me show you how that works. So right here we have a ground acceleration that goes underneath the house. The ground moves under the house, and you see how the house was originally upright. You can see that with those dotted lines. So it was originally upright, and now the house is trying to move underneath it. And inertia is causing the house to lean, and is also going to want to cause it to slide off the foundation right here. And that, of course, that's what a retrofit is to prevent. Now look, this is the exact same thing as if an earthquake force were pushing against the house. So you see how it is upright here, and then it gets pushed on, and then it's going to lean like that. So now this image and this image are identical, except one is caused by earthquake force moving underneath, one is caused by earthquake force pushing. Now that pushing force is rated in pounds of force. So all hardware is designed to resist a certain number of pounds of force. That has to do with plywood, bolts, any type of hardware at all. So what we do in every single retrofit is we figure out what the pounds of force will be, and then we figure out what type of hardware we'll need to install to resist that same number of pounds of force. So basically it works like this. This force right here, this ground acceleration, we translate that into a pounds of force that are pushing on the house, and then we take that number and then we come up with the hardware we need. So in Standard Plan A and the other retrofit guidelines we're going to look at, they used a nailing pattern on the plywood such that it would resist 380 pounds per linear foot. And let me show you where that came from. So this is a table from the building code that Standard Plan A used when determining how much strength the plywood should have. So it has a panel grade of APA rated sheathing. It's 15/32 thick, which is the same as 1/2 inch. The nails will penetrate 1.5 inches. The nail size will be 8D. That's simply a type of nail. And the nail spacing at the panel edges will be 4 inches apart. When we put all that together, we end up with plywood that can resist 380 pounds per linear foot. There's a table in Standard Plan A that looks like this, and it tells us how to figure out how many linear feet of plywood we need to put on each side of a house to consider it retrofitted. So the first thing we look at is the square footage of the house. We come down this chart, there's all these options, and in this case we're going to say we're looking at a 1,200 square foot house. And the next thing we look at is what's it made out of. And so for that, we come up here, we look, is it a stucco on the outside or is it plaster on the inside? Either one of these variables will put us into what's considered the heavy category. So now we have a 1,200 square foot house. It's heavy because it's stucco on the outside or plaster on the inside. And we come over here and we figure out the linear footage of plywood on each side of the house. And we come down right here and we end up with 20 linear feet of plywood. So that means each side of the house must have 20 linear feet of plywood to be considered retrofitted according to Standard Plan A's standard. So to see what they're trying to achieve from an engineering point of view, we just take that 20 linear feet, we multiply it by 380 pounds of earthquake resistance provided by each linear foot of plywood, which we just looked at, and that gives us 7,600 pounds of resistance is now provided for on each side of the house. So that 20 linear feet is put there so that the house can resist 7,600 pounds of earthquake force pushing on it on all sides of the house. So naturally, it's important that the nailing of the plywood in Standard Plan A provides 380 pounds of earthquake resistance per linear foot. And we're going to look very carefully at that and see if it has in fact done that. And before then, we're going to go ahead and look at some other guidelines and see how they nailed the plywood and see if the Standard Plan A and these other guidelines are the same. This is the first instance I'm aware of where there was a construction detail that showed nailing of plywood in an official document. This comes from the guidelines for the seismic retrofit of existing buildings, published, I believe, by the Structural Engineers Association of Southern California in I believe in the 70s. It was quite some time ago, and I was given a copy when I went there for a seminar in the mid-90s. And the reason I'm so aware of it is that I remember looking in the front and there was a list of the engineers who had put it together, and I thought, man, I sure would like to meet those people. And the chair, his name was Jim Russell, and I happened to track him down, and he lived in the Bay Area at that time. And so I did some work with him. I showed him some work that I had done, and he looked at it and thought I was doing some pretty good work there. And then I told him about some problems I saw out in the in a lot of the designs I was seeing, especially done by contractors and engineers. It just wasn't making any sense from what I saw underneath the houses I looked at. And I made him very aware of this, and then he just said, hey, let's put the Standard Plan A committee together. Got a bunch of building officials and all these organizations that I showed you earlier. And we put, they all got together and we made Standard Plan A. So this is the first place you'll see it, and it is so interesting that he is the chair of the committee that was also the chair of the committee that put together Standard Plan A. So these original engineers in Los Angeles, some really, really high, really good people. You might know some of them. Ben Schmidt was one. Nels Roseland, who trained me, was one. A really great, excellent engineers. But anyway, they put this together, and let's go ahead and see what exactly it is that they did. So what they had, the main thing here is we see that the 8 penny nails, 4 inches on center on the edges of each individual piece. So that means each piece of plywood will be nailed like this. And the really critical thing here that is important to know is this edge nailing right here. You see how these little dots right here, there's a dot here, a dot here, a dot here. All those little dots, that all represents edge nailing onto the plywood. So that's the edge of the plywood, just like it says right here, all edges of each individual piece of plywood. Now there's 2 top plates here. There's the upper top plate right here, and then there's a lower top plate right here, and all the nails go into the upper top plate. And that's what's so critical, and that's where we see a difference between this retrofit guideline and some of the other guidelines. So notice again how the plywood is nailed with 8D nails at 4 inches on center on edges. That was the intent of Jim Russell when he put Standard Plan A together as well. And that's what we see in the California Building Code. Remember, we just looked at it, where if the nails were put 4 inches apart on the edges with 8D commons, that we would get that value of 380 pounds per linear foot of resistance to earthquake. So that was the intent of Standard Plan A, and the construction detail for the plywood nailing should have been exactly like what you see here, and it's not. And to tell you how this happened is actually pretty interesting. Jim Russell, when he did the original calculations, he was the original chair of the committee. Well, he did the calculations and he got really sick. And when he got really sick, he had to drop out. He didn't come to any more committee meetings, and it was taken over by a building official who, was not near as conversant in wood frame retrofitting as Jim was. And so when he took over, somehow the construction detail changed. So we don't have it. The construction detail of the plywood nailing does not look like this one anymore. It's nailed, and we'll take a look at that. But before we actually look at that one, we're going to look at what all the other ones are throughout the, in the entire country. We're going to look at every single seismic retrofit guideline and see how they nailed it. And what we're going to see is that they all go back to this particular detail right here. They all have 8-penny nails at 4 inches on center on the edges. They all intend to have this 380 pounds per linear foot of earthquake resistance whenever they nail up the plywood. So we're going to look at all that right now, and then we're going to check and see what it is that Standard Plan A did that was so different, and what a dramatic impact it had on the ability for Standard Plan A to be a premier retrofit standard that it was intended to be. So in footnote 4 of table 4.4.1 in the 2008 special design provision for wind and seismic, it states that the nailing should go into the upper top plate only. Basically what it says is that wood structural panels shall overlap the top members of the double top plate and bottom plate by 1.5 inches, and a single row fastener shall be placed 3/4 of an inch from the panel edge. And that means panel edge means, you're 3/4 down from the top of the piece of plywood, go straight into the middle of the upper top plate, which is only 1.5 inches thick. So they're recommending 3/4 of an inch right in the middle. American Plywood Association says 3/8 of an inch is okay, but subsequent tests have shown actually you get a little more capacity out of a 1/2 inch. So anyway, this provision did, you can see it permeate all the seismic retrofit guideline nailing patterns for the plywood, because they do specify that the nailing should be in the upper top plate, except in Standard Plan A, and we're going to see how that happened a little later. So historically, this is the next retrofit guideline that came into existence in Los Angeles. And again, you can see it has 8D common nails at 4 inches on center at sheathing edges. OC stands for on center or apart. And sheathing is the same thing as plywood. So again, this was intending to resist 380 pounds of earthquake force for each linear foot of plywood, just like we saw previously. This is from the City of Seattle retrofit guideline. And you can see here we have the exact same thing. We have the edge nailing all along the upper top plate here and the upper top plate here. Even though I don't show that here, the nailing pattern here again is at 8D commons at 4 inches on center, just like the other guidelines. So this actually took the information from the original precedent of the California Existing Building Code guidelines for retrofit existing buildings and made a new drawing, which I think is much better. It's much clearer because it shows the upper and the lower top plate and the way it was nailed. It also shows the shear transfer ties. And the shear transfer ties, notice the shear transfer ties, the nails that go into the shear transfer ties in this direction down that way into the upper top plate, they only go into the upper top plate, which is why these nails here are only going into the upper top plate as well. So this framing anchor, also called a shear transfer tie, is connected to the upper top plate, and the plywood is also connected to the upper top plate. And we're going to see the reason for that when we actually take a look at the Standard Plan A detail. This is from the City of Portland retrofit guidelines, and this construction detail is not very clear, and it was actually lifted from the Los Angeles retrofit guidelines, but it shows the exact same things. We have 8D common nails at 4 inches on center at the sheathing edges, and so this again is a plywood pattern, nailing pattern that is supposed to resist 380 pounds of earthquake force for each linear foot of plywood. So this is from FEMA P1100. That's the most recent retrofit guidelines from 2019. And then you can see that the nailing is only in the upper top plate. So this plywood nailing is just like it was for the guidelines for seismic retrofit of existing buildings that was published in the 70s or so. So we've gone back about 50 years to the way it originally came out and the way Jim Russell actually originally intended these plywood nailing to be. So you can see it very clear here. It says provide all required nailing at upper top plate, and you see the nails right across here along the upper top plate very clearly. There are a few nails here at the bottom. There's one here at this lower top plate, one here, and I actually was curious about this, and I talked to the engineer who had helped put P1100 together and asked her, why are those there? And she said she really had no idea at all. But there was another engineer involved, and that she would ask him and find out. I never heard back from her, but apparently, it certainly won't hurt, but they're not required. So anyway, what you see here is what Jim Russell originally intended for Standard Plan A. Many people may not be aware of this, but the hardware manufacturer Simpson Strong-Tie also has a plan set, and it is just like all the other ones. As you can see, we have 8D common nails at 4 inches on center on all edges of each individual piece of plywood, and all the nailing is on the upper top plate. Again, this is to resist 180 pounds of earthquake force for each linear foot of plywood. Now, for some reason, Standard Plan A committee decided to change things. Jim Russell's intent was that nails should be on the upper top plate only, but for some unknown reason, I have no idea, they decided to put the nails on the upper top plate and the lower top plate. Now, as I said, Jim got really sick. He wasn't able to see this to the end, and I'm sure he would not have approved this if he had seen it, but that's what we ended up with. Let me show you why it's such a problem. So this is, again, our upper top plate, and then this is our lower top plate. And you see how these are 4 inches apart along each plate. So here we have one, and then we have one right here, that's 4 inches, and we have one here, that's 4 inches, 4 inches, 4 inches. So in effect, along the entire upper top plate, you have a nail that's every 8 inches. Now, the building code does not even have a table that recognizes shear walls that are nailed on the edges at, every 8 inches. But anyway, that's what we got. So the way it would actually work is, this is a floor joist. And a floor joist is a part of the floor. It supports the floor you walk on. And what happens is, when this slides this way, we want to keep that from sliding. So what we do is we take this piece of metal right here, it's called a shear transfer tie, and we nail it to the joist right here, and then we nail it down here into the upper top plate. Now, the upper top plate is only 2 inches thick, or 1.5 inches, usually 2 inches. The nails that come in here are 1.5 inches. So all the nails go into this upper top plate. So what that means is, earthquake force comes this way, pushes on the shear transfer tie, that goes into the nails that again are only 1.5 inches. So that force goes into the upper top plate. It pushes it that way. Then that force goes into the nails that are also in the upper top plate. And then eventually, when this piece of plywood pushes on the top like that, the bottom of it also pushes that way into the bolts. So these nails here on the lower top plate, they're not connected to the shear transfer tie. Therefore, they are not doing anything. So anyway, that is the problem with Standard Plan A. So, as you probably noticed, all the retrofit guidelines ultimately referred back to Jim Russell's original work in the guidelines for the seismic retrofit of existing buildings as far as the plywood nailing goes. They all recommend 15/32 plywood. They recommend 8D nails. They recommend 4 inches on center on the nailing, and they recommend nailing into the upper top plate only. We don't see that anywhere else except for in Standard Plan A, and also in this particular guideline I'm going to point out right now. So the other guideline where we find the double top plate nailing is in FEMA DR-4193. And as you can see here at the upper top plate, we have a nail every 8 inches. In the lower top plate, we have the exact same thing. So overall, the edge nailing is every 8 inches on this piece of plywood right here. Now, I talked to the engineer who, actually I work with him professionally, who was actually one of the members, one of the engineers who worked on this. And he told me, I pointed this out to him, and he said, man, that was a big screw up. Yeah, only the nails in the upper top plate are the ones that are going to do anything. And he was apologetic, wasn't quite sure how it got past him, but it did. And the real reason why this was even considered is because of Standard Plan A. Standard Plan A was a precedent. It's kind of like case law. Standard Plan A had been, in their mind, had already been hashed out. A bunch of people had been, talked about it a whole bunch, and they finally figured out that this double top plate nailing was a good idea. And that's why it's allowed here in FEMA 4193. It says that this effort would not have been possible without prior development of the following documents: Standard Plan A, Residential Seismic Strengthening Plan. So that is why we find this in FEMA 4193. It wouldn't be there otherwise. So then the real question is, well, where did it come in Standard Plan A? And what you see, continually is that a certain standard will influence the development of another standard, which is what it should do. And in this case, Standard Plan A was influenced by another document, but it was not a code document. It was not even a government document, and we'll see what that is right now. So this is the final case where I could find nailing in the upper and the lower top plates. This comes from the Simpson Strong-Tie catalog. This detail was in their publication from 2007 that was for homeowners for the retrofitting of their homes. And it's what they use to sell hardware. The manufacturer, the people who drew these, they didn't know anything about engineering or retrofitting or anything. He just, he put this detail up, and it looks nice. I mean, even the extra nailing at the top, it's attractive. So this must have been used by the people who are putting Standard Plan A together, because there's no other way that they could have come up with this. There's just nowhere, you don't find it anywhere. There's no code references. There's not in the California Existing Building Code, not in the Los Angeles Building Code. There's no precedent for it. So the only explanation I have is that. And the interesting thing is, I do recall at one of the meetings where the building official from San Leandro had talked about how he had hired someone who worked for Simpson Strong-Tie, making their drawings like this for them. So either that particular person had already drawn a detail like this, or he was fully aware of it and would have also had a tendency to draw the detail like this. So that's why this detail is in Standard Plan A, and it's the only time you ever find it. And actually, it's a little bit on the crazy side, because if you think about it, this was not put in because of any engineering expertise. When you get down to P1100, where there is some true engineering expertise, as well as Jim Russell's original design back in the guidelines for retrofit of existing buildings and the California Existing Building Code, those are all rational. But this one, it just came about because of some quirk, some human error. And this is just to show that even though it looks like scientists with white coats and microscopes and things, or they're writing codes and things like that, it's just human beings. And sometimes things like this just happen. So right here I've listed all the guidelines and shown which ones recommend the upper and lower top plate nailing, and the ones that recommend the upper top plate only. So the first case I could find where I saw the lower and upper top plate nailing was in the Seismic Retrofit Guide for Raised Foundations, published by the Simpson Strong-Tie Company. The oldest one I could find was from 2007. Standard Plan A was, all the details and things, I believe, well, they were put together in 2008. That's the revision that I have. So the only thing I can imagine is in 2008, they were looking at this guide And out of that, they decided to put the upper and lower top plate nailing in. I have no other explanation. There's no engineering basis for this. If you look at the other guidelines, at that time it would have been the Uniform Code for Building Conservation, which is the current appendix chapter A3 in the California existing building code. They didn't get the information from there. There's no telling where that came from. That's the only source I can think of, is that it came from that guide published by the Simpson Strong-Tie Company. And so then in FEMA DR 4193, it specifically states that they have incorporated Standard Plan A into their plywood nailing. It very specifically states that. And the assumption there was that the committee in Standard Plan A, they'd been debating on this for years, and they decided it was the right way to go. But from an engineering point of view, there's absolutely no reason to have this upper and lower top plate nailing, and that's the only explanation I have. And I would like to point out, because I was on the committee at the very beginning, Jim Russell, who was the first chair before he got sick, he said, we're going to look at all the existing retrofit guidelines that are out there, and that would have been pretty much, I think you're limited to the appendix chapter A3. But he said we're going to look at all the different guidelines, find out what's the best, what's good in them and what's bad of them, and then we'll take all that information and we'll start out from what we consider the best. But unfortunately, he got sick, and from that point on, we never looked at anybody's guideline. We never looked at Los Angeles. We never looked at appendix chapter A3. We didn't look at anything. We just did everything from scratch. And so we ended up with this, and from scratch, we ended up with something unique. And that is the upper and lower top plate nailing that we see in Standard Plan A. So it's an aberration. I can't see any rationality behind it. Maybe if someone would contact the former chair, who was the building official from San Leandro, maybe he would have an explanation. But the only explanation I have, I gave you already, and that was that there was someone who worked for the city of San Leandro who was putting all these details together. Was familiar with the Strong-Tie guide. So over here on this side of the upper top plate only, we have the original guidelines for seismic retrofit for existing buildings, which eventually was part of the Uniform Code for Building Conservation. Then it went into the California Existing Building Code. And this right here is kind of a big deal, this special design provision for wind and seismic, because this is published by the American Wood Council, and that is that basically drives all code decisions regarding wood. Anything that's in there is considered sacrosanct. So in that particular document, as we saw, it recommended nailing into the upper top plate only. And then we go down to all these other guidelines. The City of Los Angeles, that's one that was very heavily reviewed by some very high-powered engineers. Jim Russell was actually instrumental in that one as well. And then we have City of Seattle, City of Portland, Simpson Strong-Tie plan set. Now, the really weird thing is that the plan set has different nailing than their retrofit guide. And so this right here would have just been obviously done independently. This is when they actually had the engineers on the Simpson Strong-Tie put this together, and they, it's very obvious when someone explains it to you why you should only put the nails in the upper top plate. So that's what they did. And then finally we get the most recent guideline, FEMA P1100, that was also put together by some very competent engineers. And they also, went back to what Jim Russell originally did in the guidelines for seismic retrofit of existing buildings. And they put the nailing in the upper top plate only. So the big question is, what do we do with this information now? I'm not sure exactly how this double top plate nailing ended up in Standard Plan A. I wasn't there when they actually put the details together. In fact, I wasn't even there for the 2008 revision, so I'm not sure what happened there. The one thing I am sure of is that it is very bad engineering, and that it's making these retrofits ineffective, it's making them expensive, and it really should be revised. And hopefully the people who watch this video will agree with me and put some kind of political pressure somewhere to make sure things change.